Okay, good morning. So this week I'm going to cover chapter 3, which is on processes. The slides are up to part 1, which really covers two major concepts in this chapter. This is a huge chapter. And there are two parts. One is really the basic concepts on processes themselves. The second part, which I'm going to go into, is really on what's called interprocess communication. That is, how do different processes talk to each other? So there's really these two distinct parts in this chapter. And I personally think they should be broken into two separate chapters, but that's okay. And then next time, I'll cover more of the specific examples of how real systems use these interprocess communication, because there's just so many of them. Okay, so this is kind of a rough outline, but really I'm trying to follow the textbook order because there's been some adjustments in the textbook. And so here, so really this chapter wants to go into more of the detailed notions of a process. And what is a process and how is it different from a program? So a process really is a running program, you can think of it that way. And in fact, a program you can think of as just the image, the executable code, right? It's something more static, it's passive. Whereas a process is that program being activated, running, it has memory, it has resources, it has state, right? Whereas a program is just kind of read-only data. Could be on disk, could be on in your RAM or so forth. Now, there's different features of the processes that the OS really need to implement. So certainly the creation of a process, termination, and scheduling, because the whole point of creating a process is so that you can schedule it, run it for a while, maybe put it aside and run another process. And there are many ways to do that. And also support communication, which is the second part of this chapter. So there's a lot of exploration on the different ways you can do interprocess communication. The two major ways are what's called shared memory versus message passing. We saw this in previous chapters too, but we'll go into a lot more detail here. And part of doing communication is really leading to client-server type, and that's mostly done in message passing. Okay, so basic concepts of processes. So as mentioned, the program is really just executable code, right? Think of it as your compiled binary, your hex file, your whichever .exe file, the COFF, the COFF common object file format, or there's different file formats that have been proposed. And so it's a static concept, whereas a process is, say, you want to launch a program. So what happens? Well, in the case of an OS, then OS needs to set something up, set up that running environment with basic resources, load it in, and then start running it, right? So that setting up is done by OS. It's mostly transparent to the user. User doesn't really think of it that way. They think they run just that program. And then potentially you can have multiple processes all running the same program. What do I mean by that? So consider a shared machine, right? Everybody is doing their assignment, like in the old days anyway. You might be running your editor, could be VI, could be Emacs, or something. There's 100 students in the class. They're all running editors. So that means there's 100 copies of VI or something running, or you compile with a C compiler. You're compiling, I'm compiling. And, well, so what's an OS to do? So that means OS has to create different processes for each user, right? Otherwise, if I'm running the C compiler, it reads in my program into the program memory. And when you invoke your C compiler, it's the same executable, but it better run as a separate copy. rather than using my copy. Otherwise, you'll be compiling my code as opposed to your code, right? So there's that notion of processes. So you can have several distinct instances of processes all running the same program. Understand that? Okay, so so you can think of as program kind of like class and process kind of instances, right? That's, I mean, one rough way to think. It's not an exact analogy, but that's kind of the idea. So processes is a program running. So that means it has its associated data, state, permission, user, everything, right? But you say, hey, but like on my app, if I just press like Chrome or my map, it always comes back as the same one. Yes, that's a UI, that's a shell restriction. It figures out, have you already started this process? If so, it switches to that process, okay? And then if not, it launches it. So to you, you always work with an instance. That's a simplified user interface, right? That's a UI artifact. It's not how processes work. So in a text command line interface, you know you can certainly launch an instance, or you can start another instance of a shell which runs in its own process too. Or you can put a job in the background and then start another job running it, and then so forth, right? So that means you can have multiple instances or multiple processes that all run the same program executable, but each one is a distinct instance, and they each one has its own memory address space. So when it touches memory 20, it doesn't affect the memory 20 of another instance of the same program, okay? Unless you really want them to. Then that's later. We'll talk about shared memory type of interprocess communication, okay? But otherwise, it's an independent instance. And if it crashes, doesn't affect any other copy. But that wasn't true in the old days, like DOS, for example. Okay, so now, process is really the standard term in textbooks in most places. But as you know, people did their own system over time, and they just picked whatever terminology was appropriate at the time. So process wasn't the only term that's been used to describe that concept. But now let's standardize on the term process. There's certainly other terms used, but from possibly a different domain. So job is another term that's used as a process. So in Unix, you can have a foreground job, background job, things like that. That job refers to a process. And because the Unix went way back to 1972. And during those days, most of the scheduling work was done in operation research. Anybody knows what operation research is? You find operation research in, say, business school. So what do? They would do like factory scheduling, right? Job scheduling. So assembly line. They say, okay, I have an assembly line, say make cars, make something, right? And you divide job into different stages. And do you feed this? How many assembly line stages do you do? And what time do you allow for each stage? So that's scheduling. That's done way back, right? So this is like 100 years old or even longer since they had these mass production. So operation research or job scheduling, that's very mathematical, but that's done in business school. And certainly early days of OS, people say, okay, we need to do scheduling. What do we do? So they look literature search and then found, wow, this is all in business school. So they went and borrowed a lot of concepts from business school. And they call those jobs, right? Because job is for a person to perform or for a machine to perform. And later, over time, this concept got more refined. And process is now the preferred term. But when you see job, it's synonymous with process. But you should try to use process instead. Now, another term called task is also used. But this term came more from, say, real-time systems people. And so there, it's kind of a funny concept. Because in real-time system, what happens then is you have these real-time tasks that need to be scheduled and dispatched, and has to be done before deadline or after release time, things like that. So real-time systems, they are really distinct from OS people, even though there's some overlap. And then they're much more mathematical. Because they need to prove strictly that you can meet these hard deadline constraints. And their convention there is really to call these tasks as opposed to processes. Processes is more of a general OS concept. However, the term task kind of gets stuck in several ways. So Linux, for example, they didn't really use the term process. They used the term task. Why? I don't know. Ask Linus, the author of Linux. I think there is a reason, because next chapter, what you'll see is the concept of threads. Now, threads are lighter weight processes, if you will. In other words, threads allow you to run concurrent things, but within the process. So it's much cheaper to start a thread as opposed to a task. But to Linux, they say, well, seems like the same concept to me. There's just some minor differences. Let's just call them tasks. Okay, so that's kind of what happened. So now the task, it may be slightly lighter concept than a process. It's intentionally vague. Okay, so but a process very specifically has its own address space. It's a resource. Think of it as really a distinct protected copy. Now, the word task also means something slightly different in that it is really you can think of it not so much from the program point of view, but from the user point of view. So it's what the user needs done. So that would be a task, okay? As opposed to OS concept is more like, oh, I only know how to run program, kill program. I don't know if I need anything else. So task has this higher level connotation of what the user wants, as opposed to what the OS knows how to do. OS doesn't know how to solve your problem. It doesn't know how to pick up your laundry. It doesn't know how to make you a sandwich. It only knows how to start task, stop task, right? So then the task here, again, is used intentionally vague as something that needs to be done. Okay, as opposed to a process, which is really purely OS concept. Okay, let's just get that out of the way. Okay, then let's focus on process in memory. So memory is a key concept. If you want to run a process, you gotta give it memory. Otherwise, it's not gonna work. Memory for what? Well, code takes up space. Code takes up memory, right? And well, in the case of embedded, if it's like, okay, fine. The code is in a separate code bank, but fine. That's memory. But for most machines, von Neumann machines, remember von Neumann machines? Program data in the same memory address space, right? So some part of RAM is taken up by your code, and it's loaded in, okay? And now, so this is a typical way, say, a Unix running C program organizes its memory. And pretty much everything else can be written in C, and then on top of that, right? So everybody else pretty much follows this order. So what do you have? So at the bottom, you have the address starting from 0 and up. And that's what do you put there? Well, you put code. But in memory terminology, that's called a text segment. Say text, I mean, do you mean ASCII code, human readable? No. In process terminology, text means code, program code. Okay, binary, the code you can run. Program your assembler outputs, linker loads, linker links, and then loader puts it in. So it starts from lower address. Kind of natural, right? Because on program reset, where does it jump to? Your interrupt service routine, all at the lower address, right? Most likely. So that's kind of a natural place for your code, right? And 8051 certainly does that, starting point from 0. Now, after text, well, what do you put after text? Well, you can remember we had that jump table, right? Or that lookup table for 7-segment LED. You put after that, right? So you can have read-only data, or you can have global variables, right? I mean, in C, you declare basically outside your braces. That's all globals. Or you can have static as well. And then after that, as you increase in memory, then so the globals are what's called statically allocated variables. Then what do you have? Well, not much. So it's called heap. But this heap is different from your data structure heap. Remember data structure heap? That's kind of a priority queue implementation. It's like an array implementation of a tree, but the elements are ordered so that the upper level is less than equal than its children, right? And then you can do that. A heap extract takes login time, heapify linear time, and to restore heap property login time. And so that's the heap, but that's not that heap. This heap is purely for dynamic allocation. What does that mean? Well, remember your malloc free from C programming. You say yes. So yes, that's when you malloc allocate request dynamically, like your linked list. Remember, a lot of times you say, okay, let me do a linked list new, and then in C++ it will be new. In C, it will be malloc, right? In size of the struct. That's how you dynamically ask for, and then free puts it back. So, and anytime you do like object-oriented class instantiation, right? That takes it from heap. And so that's where it's dynamically managed. You can give it to some program segment that when they're done, it's freed or deleted and takes it back, recycled, used for some other purpose, right? And you have big chunk of empty space, and then all the way to the back, the top, the end of memory. That's for stack. It's like, what? Stack? What's stack for? Well, remember, when you do a function call, you need a runtime stack, right? Why? Basically, minimally you need a return address, as we've seen in the call return, right? That's pushed on the stack and popped from the stack. What else? Well, when you pass parameters, that where does it go? Well, you can have recursion. If you don't have recursion, no need to do any stack, other than the return address. But every instance, if you call a function, either itself or somebody else, pushes what's called activation record on the stack. And then what goes in there? Well, your parameters. What else? Your auto-local variables, right? In C, you have local variables, right, after braces. And then inside, you can have even more braces with more. Those are called auto-locals. Why? Because they're automatically allocated and deallocated. When are they allocated? When you enter the brace, allocated. When you leave the brace, deallocated, right? And then because this is in stack order, right? You call something, and then it keeps calling something, right? Just keeps pushed on the stack. And then when they return, who returns first? Well, it's the last one that gets called that returns first, right? So they get popped. All natural, right? So a stack is perfect for that. So, but then that's something that needs to be allocated dynamically, but in the structure. Whereas a heap is more or less unstructured. Why? Because when you leave a function, when previously you allocated some memory, that sticks around. It still occupies space. It's not like when you leave a function, your dynamic allocation, your object goes away. No, unless it's a local variable, right? If it's scoped locally, yes, they push it on the stack. And then when you leave, pop it. But if you new something or malloc something, even after you return from the function, it sticks around, okay? So then dynamic allocation, that's much more complicated. Whereas a procedure call return, that's easier with a stack. And so they are both dynamic, but with a very different characteristics. That's why you need kind of that free space in the light blue there as kind of this buffer zone. And hopefully your stack never crashes into your heap, all right? And if stack and heap collide, what happens? Really bad things happen. Your program will go haywire, okay? So that's why you keep them as far away as possible. You hopefully they don't crash into each other. So how do you know? You don't. So you have to rely on something. Well, certain instruction set architecture provide a little help. So they have certain bounds check just when you do the push and pop or return and so forth. That because you know those are accesses to the stack, right? And so every time you change stack size, it checks, hey, where's my heap? Am I running into within some safety zone, right? So if it tells you when it collides, that's too late. So usually there's a little buffer zone, okay? So when you are some distance away, you say, oh, warning, warning, better be careful, okay? So that way it can catch certain of those things. Otherwise, if you just keep running and they collide, you have no idea. Okay, so that's one thing that needs to happen is that check. And hopefully these address bases are large enough that this is not an issue. But you can imagine a program that goes into recursive calls itself, call, and then stack it, pretty soon runs into a heap, and then your program just goes bad. So that's why there's usually a limit on your recursion depth, right? Sometimes when you run a program, you can try it that's on your own computer. So just have a function call itself infinite time, no base case, just keep running. And then at some certain point, it might tell you, recursion depth exceeded. Maybe not. But this is something that a lot of Unix systems actually support, is they will periodically check your stack depth. And if it exceeds certain stack depth, and that's way before it collides into a heap, then it tells you, sorry, you can't use so much stack. It's too dangerous. Okay, they catch it. But you can set that limit. I know what I'm doing. Okay, so then you can set the stack depth to something else. Anyway, so this is just memory. But a process actually has more state than its memory. What are those things? Well, remember, a process can request OS to do services for it, right? When you request OS to do service, what happens? OS would allocate some resources. Not just memory. Memory is one form of resource. What else? Well, there's anything. It could be, I'm using I/O devices. Yeah, that's a form of resource. I'm using files. That's another form of resource. Who keeps track of these things? Certainly not the process itself. OS has separate tables just to keep track of those states. They're not in this process's memory space. They're OS. Why? Because if it's in my own process space, I go ahead and change whatever I want. You open the file, I change it to a different name. Suddenly I have access to something else. That wouldn't work, right? Better be in some other table where OS cannot touch directly, but needs to make system calls so that OS can do that on behalf of that process. That's protection, right? So process state. Now this is from OS point of view. What are possible? Well, these are kind of rough concepts. I mean, an OS doesn't have to have a label called new or ready or running, wait, or terminate. No, this is just conceptual. And when somebody draws a diagram, roughly these are the 5 states. There could be more, could be less. So new is when the process is being created by OS. So it just says, okay, now here, ID. And I know I am going to create this one. It's still being created. And after it sets it up and then copies the program memory, or at least set it up, then ready to run. So that means anytime the scheduler can decide, oh, now I'm going to run this process for a while. That's ready. Okay? So it would pick from a list of ready processes. Now, on a uniprocessor, you can be running at most one process at a time. I mean, there could be others ready to run, but they are kind of put in the ready queue, not really running. So one process is being running at a time, right? So that's in running state. What about waiting state? So that means that process it's probably running for a while and then it makes a request, such as I/O. So like, for example, you have a web server and then it says, okay, now I'm ready to take more requests like HTTP. I'm going to serve some web pages. I have nothing to do, right? And there's no request coming in. Then that process gets put in waiting state. Why? It's waiting for I/O to come in. It's just sitting there. Well, it can't do anything else, right? It's waiting, okay? Or it could be I/O. I'm reading a file, but I'm waiting for the disk to spin around. To us, very, very fast. But to a computer, right? So 1 millisecond is a long, long time, right? And these things can take hundreds of milliseconds, if not longer, right? So while it's waiting for that just to be read, has nothing else to do, just sitting there. Should it just be running and doing nothing? No, it should just be put aside so somebody else can do useful work, right? So if it's waiting for some service to complete, it's in waiting state, right? Now terminated, that means the process somehow finishes or gets killed. So either it dies by itself or somebody kills it. So OS is kind of violent world. So, but anyway, so later we'll get into more violence on these processes. You can kill the process, you can do all sorts of things. Now, but in terminated state, what happens? Well, somebody has to clean up the junk, right? Just like, well, there's a dead body, you don't have to bury it somehow, right? You can't just leave it taking up resources. Okay, so diagram of a process state. So those 5 states: new, ready, running, waiting, terminate, right? So you need to know the transition. So new, somebody creates, could be a shell, could be something, right? A process could actually create some other process. Then creates it, sets it up. Oh, now it's ready to run. Puts it in ready state. Okay? And then running happily, and then what happens? Well, so it could either make a system call. That's when OS gets control back. Okay? And when it makes a system call, that's when the OS says, oh, okay, now it's my chance to steal your control back. I'm going to put you in ready state, right? So, or next one, pick somebody else from ready state. It could be in a queue, could be in FIFO order, that's called round robin, or it could be some prioritized scheme, right? So that's what a scheduler does, or dispatcher. Now, scheduler is the one that decides who to do, and dispatcher is the one that actually does it, and pulls from ready queue, makes it running. And of course, before that, somebody running has to be stopped, save state, put back into ready queue, right? And if it does, it has to running. Well, running when it has I/O, then goes to waiting. What else could happen to force a running process to go to ready? Well, the timer interrupt, right? So because otherwise, if I write code, I never make any system call. Do I just keep running? No, the OS. Preemptive OS can steal your control back by using a timer interrupt, right? And running could go into terminated state. That's with a normal exit. There's actually another possible transition. Could be from ready to terminated, so if it gets killed, but it's not shown on this diagram. Or while it's waiting, could also get terminated. That's not voluntary exit. It's just somebody gets killed. Okay, yeah. No, interrupt happens without any control, unless you do a system call. So interrupt here covers system call. So if you do running and then you make a system call or timer interrupts, you go to ready state. But okay, I should take that back. Interrupt basically steals control back, and if it can be completed right away, then yes, it just puts in ready state, depending on how you implement the OS. I/O is when you make a system call and then says, oh, sorry, I can't return right away. It's going to take a while. Then OS has a decision. I can make the decision and say, you got to be in waiting state, because next time the scheduler comes around, when it wants to pick, it can pick the one that's still waiting. All right, so because it's still waiting for I/O, there's no point trying to test it and then go put it right back. Right, so ready means it really has everything and not waiting for anything else. Okay, so that yeah, I mean, I think that's more of an implementation specific decision. But at least interrupt is, you can think of it as kind of a, in this case, think of it as external one as opposed to system call, because system call would then most likely maybe glide through waiting if it can be completed quickly and then goes to ready. Okay. So yeah, this is really just more of illustration than exact state diagram. Okay, so remember the process state is more than just its own memory. There's something called PCB or process control block, and sometimes called task control block. obviously because like Linux uses the word task instead of process, so they call it task control block, but this is process control block. So this, think of it as a struct, right? Or maybe variable size struct with an open-ended back. And what does it do? Well, this is a data structure kept by the OS, okay? Not the process itself. OS does this. And what does it do? Think of it as a big linked list, right? And so it can, one process control block can link to the next one, link to the next one, link to the next one. Why linked list? Well, because as you can see, when you transition between states, you can put into different lists, right? For scheduling purpose, for ordering purpose, whichever. And then process state could be represented explicitly, or maybe it doesn't have to be. So you could have an enum type that says 0 means new, 1 means ready, 2 means running. You could do that, but that we don't really need to worry about that. Process number, well, yeah, that most processes get identified by a process ID or PID, which is an int, and that uniquely identifies a process that's currently somewhere in one of those states. What else? Well, so remember, you need to save, most of the process, except the running one, need to know where they get stopped and where to continue, right? So you need to say what? Program counter. That means that program counter is where you are in that program, right? Also, registers, right? In 8051, you have R0, R1, R2, and all those, right? Even accumulator and a bunch of others, right? Registers, why? Because those store temporary values in your computation, right? You may need one that's a pointer, one that's partial sum. Those are CPU registers. Now, what about special function registers, like your P0, P1? Well, no, those are volatile. No. So somebody else controls the use of those, but and certainly timer you can't. You could do a snapshot to remember the time, but you don't restore it. Memory limits, so those could include various types of memory management. So, for example, I was saying your stack, right? Your stack may have a limit. If you go over that limit, OS may catch it. You're going to crash into your heap, right? And maybe other things too. Maybe you want to do a protection on your code. You don't want the programmer to have to be able to modify code. So even though it's in the process's own address space, OS may enforce certain limits and say, no, you can't write into your code space. That's too dangerous. That's self-modifying code, right? So OS certainly can modify itself as it's bootstrapping, but no, user process normally shouldn't be allowed to modify its own program code. So it could set some limit on there too. So those would be the kinds of memory limits you could place. Plus other resources. But here they just say list of open files. And a lot of times in Unix systems, I/O is treated just like a file, kind of API. So they would probably include that in there too. What else? Well, there's more things that are not shown here. Could be just whatever the system may track. So for example, your accounting information, like how many CPU seconds or minutes, CPU time used, time elapsed, so that's more the real-time stamp, and time limit, and so forth, right? Accounting, so they might charge you by the hour. Certainly a priority could be in there, right? So I'm paying more money, I should get more CPU cycles, proportionally speaking, right? So yeah, or maybe I'm a real-time task, so it could be in there too. So any information you might want to keep track of for each process that goes into the PCB. Yeah.
What does it mean you said the process control block?
Yeah.
Next PCB.
Yeah. So this is basically a linked list kept track of by the OS. So next process would have a PCB in the OS, right? And then so OS does the linking and moving these PCBs around, like from ready queue to waiting queue or something.
Okay, that's
Yeah.
the pointer to
Yeah. To whichever list it's on. Yeah.
Like another process.
Yeah. Another process is PCB. Yeah. Okay. Now, so processes are kind of heavyweight, right? Because think of all the steps it has to go through. The OS has to create a PCB, that's a struct, and fill in all the information, and then make an address space for it, and then there's a context switch. That's kind of heavyweight. So people figure this out and say, oh, I want something lighter weight. And so that's what threads are. And next chapter, chapter 4, is all about threads. And in fact, this course, you'll do a project on threads. And so you'll have plenty of time to know about threads. But think of it, for now, just as lightweight processes. What that means is you can think of as concurrent units within a process. So they share the same address space, same resource, same code, same everything. Other than each one has its own program counter, its own stack. Like, what? How can you just said a stack. There's one stack, right? Well, yeah, there's one to run the program, but then each one has its baby stack, and you allocate in heap. Oh, so it's dynamically allocated, and then when it's running threads, that stack pointer gets moved to its baby stack, and it's running for a while, and then your threads package has to do a switching, and then say, oops, okay, now I'm gonna move stack pointer here, and then it's running in its baby stack, and for a while, and then switches. So it's all in that same address space. But you say, hey, but you just said the stack may crash into the heap, right? Well, yes. So that's why you need to set the limit in those special cases. So that it allows it. Okay, so I know what I'm doing, so leave me alone. I'm gonna do my own threads. So, but you get plenty of fun later with threads. Okay, so multiple threads can belong to one process. It's much lighter way, right? Because you can switch between threads without having to do a big context switch at the OS level. So, yeah, so we will do threads later, and threads are really a lot of fun. Okay, so you should know what a process is, different synonyms, process, job, task, right? And also a difference between process and threads. Well, but we'll come back to threads next chapter. And possible process states conceptually, what a PCB is, its content, and context switching. Okay, so we'll do context switching next, which is, related to process scheduling. So what's process scheduling? Well, you have these processes, and let's just even focus on the ready ones. That means any one of them can run, or are eligible to run. In other words, they have useful work to do, they're just sitting there. So somebody has to pick them. That's a scheduler. The scheduler is one that picks them, and then a dispatcher is one say, okay, this is what you pick. Let me take out the other guy and then put it in, and let this one running, right? But in OS terminology, a lot of times what they do is they mix the terminology. So they say, scheduler. Well, scheduler that does both the decision, which is the scheduling part, and the dispatching. They often mix these two, but really there's that distinct difference. For OS, it's really for multiprogramming by maximizing CPU utilization. Right, so you don't want a process to just be spinning, doing nothing, waiting, and sucking up power. Right, whereas somebody else has work to do, they should be able to share the CPU at the time. And also, you might want to provide time sharing, and that was especially important in the days when we had shared machine. Everybody all logged into one machine, doing their assignment on the same machine, and so everybody wants their share of the time. Now, even with the mobile processor or laptops, you still want to say, okay, I have something that's running, I don't want it to stop just because I switched to a foreground or background, right? So that time sharing is important, and time slicing. Scheduling means always decides which one to run and for how long. Now, degree of multiprogramming is number of processes that's kept in memory. Because there's a separate term called swapping. Swapping is actually saying, well, there's a chunk of memory that I'm probably not going to be using for a while. But I can just wipe it out or reuse it. I better save it. So where does it save? So what it does is takes that chunk of memory, save it on disk. and that's to swap out. And we'll come back to swapping in the memory management chapter. And so everything else get kept in memory, right? So degree of multiprogramming refers to how many processes do you keep in memory, okay? And because someone's, if they're maybe they're not going to finish or they exceed their quota or something, you may want to give them really, really low priority. You could swap them out to disk and then later bring them back, because for so long you're probably not going to want to let them occupy so much space. Now, there's also what's called I/O-bound process versus CPU-bound process. I/O-bound means a process spends much more time doing I/O than computing, whereas CPU-bound does much more computing versus I/O. So I/O-bound would have much more time in I/O and then shorter, relatively shorter, many short CPU bursts. A burst means it runs for a while and then either can't run anymore because it's waiting or making a separate request. CPU-bound just says long burst, so it just has more computation to do, run, and then doesn't want to do much I/O. Now, so scheduling queues. So earlier you see PCB, right, with these linked lists. Well, for good reason. They are moved between different queues. Queue is like a FIFO, right? And then you can reorder them, move them. So processes can migrate between different queues. And so, well, there's a job queue in new state, where all the processes are in the system. Ready queue, that means processes in the ready state. I/O queue means they're in the wait state. And then there may be potentially multiple of these queues. Okay, so this is a diagram kind of paraphrase from the book. So you have these potentially different queues. A CPU will be running whichever running process is, right? So you take one process at a time from the ready queue, put it in CPU running, and then while running in CPU, what could happen, right? You could make an I/O request, go to I/O queue, and then perform the I/O, and then back to ready queue. Or you could have the timer interrupt, OS gets control, and then what happens? Well, if it's not requesting anything else, well, it goes back to ready queue, right? That means if ready queue is empty, then it gets to run again. But if not, then it just goes back and let somebody else run. It could make a child process, and that's with a fork call, and then there's the wait queue requests, right? And then there's other wait queue for an interrupt, right? Now, process scheduling queue. So there's different pictures. So this is really dependent on the OS implementation. So some queue, well, as you remember from your data structure class, it would have a pointer to head minimally, and most of them have another shortcut to the tail, so that if you have to append easily, you can jump to the tail, add to it, and then adjust the tail pointer, right? And then you have different I/O queues. One could be for tape, one for disk, one for terminal, one for keyboard, one for whichever device, network card. So do context switching, what happens? Well, you have a process. So here, let's just see, you see between the process P0 and P1, time goes down. So P0 running for a while, when it's interrupt, system call, OS takes control. What does it have to do? It has to save its state. Remember, PCB has its registers, program counter, right? All those. Well, put all the necessary state into the PCB, right? And then OS does the selection. Do I have another one that I can run, right? Then it runs for a while, picks one, then restore its state. Once it's restored, it can run. Normally done with some kind of a return from interrupt. But this one, it's set up so that the stack is ready to restore the state the last time it was taken away, right? So P1, in this case it chooses P1. So restores, and then it starts running P1 for a while. And P1 gets another interrupt or makes a system call. P1 state gets saved and then picks somebody else. Could be P2, P3, whichever, but in this case, just for illustration. Then P1 gets selected, restores state, OS restores state, and then P1 P0 continues. Right? So OS is in between, saving state, picking one, restoring state, and so forth. All right? So context switch, that's context switch. That means switch to a different process for running, right? So kernel saves the state of current running process and then picks the next one to run from ready queue and restore the save state of the target, okay? But this is work, like here. The blue part takes time, and scheduling can be arbitrarily complicated. I mean, if you read the literature on scheduling, some scheduling algorithms are what? N squared, N cubed, exponential time. You can't have an exponential time algorithm in OS, right? Then it's spending all this time. Okay, I'm gonna pick the next process and I'm gonna take my time. No, it's not gonna work. It has to be very efficient. It has to be log-in time at best, right? Or even constant time would be even better. So that's overhead. Time spent by the OS and user certainly wouldn't like to pay that price. It's like OS should be instantaneous, shouldn't take any time, and because that's price to pay, that's not productive to the user, right? So that means OS shouldn't be switching too often, but at the same time, users don't have patience. I type a key, I want to see the key. You can't wait too long either. So what's the right sweet spot? Well, somewhere between tens of milliseconds. I guess tens of milliseconds is probably that right amount as far as users are concerned. But in practice, it could be 1 to 1,000 milliseconds. You shouldn't get too fine-grained, or the time shouldn't be too short, because it's a lot of time to take interrupts, and all of these involve some kind of interrupts, right? So, and most OSs really aren't so good at taking so many interrupts. 1,000 interrupts a second is a lot of work for any system, okay? Even though, it's not, like you think a millisecond's a long time. Well, this kind of context switching is expensive too. And that's not even considering the complexity of the scheduling algorithm. Time can pick the next one, right? So, and also like RISC processors, they have lots of registers to save, as opposed to 8051, 8 little registers plus a few, right? So 1 millisecond seems like, you don't want to go much faster than 1 millisecond per context switch. Tens, maybe 20 to 50 is probably the right context switch time. And for users, that's okay, because it could be screen response, could be audio latency. There's some psychology involved here. So yeah, I think tens of milliseconds is usually good. 1,000 or 1 second, that seems like a long time, right? Okay, so now what about hardware support? Yeah, certainly this is very high overhead. So certain architectures have provided support for lowering the overhead of context switch. So everybody should know about ARM instruction set architecture, right? So that's in pretty much all of the handsets. ARM does provide what's called the multi-load, multi-store, and multi-push, multi-pop. So, normally when you do a load store, your traditional architecture just does a single register at a time. In ARM, you can specify a bit mask and set of registers. And you can do load store multiple or push pop multiple. Hey, that's a lot of work, right? That doesn't seem like RISC architecture. Well, ARM is not a purely RISC architecture. But yeah, you can say R2, comma, right? R4-R7. Assembler translates into bits, so you have a bit mask associated with these. And so that way, a few instructions, it does in streamlined fashion and very good. Now, in addition, there's also register windows. So Spark architecture from Berkeley, the original RISC from Berkeley, and then which heavily influenced the SunSpark architecture. That has register windows and sliding windows, mainly for procedure calls, but for saving register and context switch, that also is helpful. So they could reserve certain ones. And 8051 is one we talk about. You might think, hey, that's a tiny little processor, but that has register windows. So it could be also used to save context switching costs, even though it doesn't have protected memory. Okay, let's take a break here, and we'll continue with more context switching.